Oh my god! Oh jeez! Oh my god!
Given the functions f of x is equal to x plus 3 times 2x minus 1 squared, and g of x is equal to 2x to the 3 plus 13x to the 2 plus 17x minus 12, graph the function h of x, or graph the function h of x is equal to f of x times g of x using properties. Okay. And then, oh, sorry. Oh, I was reading my own stream, not yours. My bad. Oh, yeah. We can go to the next slide. So,
This is very technical.
oh, did you not factor it?
Oh, we talk about that after.
Oh, yeah, you can skip this slide then. Okay, so, the first part of this question, the thing is, g of x is not factored, so you gotta factor it. How do you do that? That's a good question, me. I will answer that. So, first you want to find the factors of g of x. So, how you do that is essentially you plug in numbers which are a factor of the last term. So, all the factors of 12, plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, right? And you keep doing that until your function equals 0. So, if you plug in -2, so if you do, I believe it's, yeah, g of -2, it actually equals 0.
Oh, I did 1 over 2.
Oh,
Yeah,
okay.
everything works.
Yeah, it works. So, but uh, you can just look at the paper for what Josh did, but I did it differently.
Mm-hmm.
I did synthetic division, so you can do synthetic division for -2 or 1 over 2. I think you'll probably get the same answer by the looks of it.
I mean, it's just
So,
long division.
yeah. Uh, we both got the same answer. So 2x minus 1, x plus 4, and x plus 3. So after you do that, you have to multiply that by f of x. So you get, sorry, this is, I don't have my papers organized. It's a my bad moment.
I'm gonna explain my old slides. I'll give it a try.
Yeah, go for it.
When you're done.
Oh,
What part are
okay.
you on?
Oh, sorry, I'm combining the functions now.
Alright,
So
so
yeah.
graphing h at x to f at x times g at x. It's shown right here. Never
Yeah, this
mind, it
is then
isn't.
multiplied, right?
Oh yeah, you multiply the two terms. At the bottom right, that blue box is h at x. H at x is in 3 brackets, 2x minus 1 to the power of 3, x plus 3 to the power of 2, and x plus 4 to the power of 1. So, if we want to graph this function, we have to figure out its characteristics. Starting with 1, x-intercepts. So, x-intercepts, just simply factor out x for each bracket. So 2x minus 1, that would just amount to x equals 1 over 2. That is one of them. We also have to account the power on the bracket as well. So 2x minus 1 has a power of 3, also known as a point of inflection. X plus 3, that factors out to x equals -3. That has a power of 2. Oh, these are actually called orders. My bad. Order of
My
2,
bad.
which is a tangent. Basically, it just bounces off the x-axis. Point of inflection means it like kind of chills at the axis for a bit and then keeps going. And order of 1, which is x plus 4, which factors out to x equals -4, that just goes straight through the x-axis. Y-intercepts, to find those, you just gotta set x to 0, solve, you get -36. Degree and the sign of the leading coefficient. This is self-explanatory. Basically, if you add up the orders for all of the brackets, so you got 3, 2, and an invisible 1, which you don't need to write down, you get a degree of 6. And a degree of 6 would result in a hextic function. Hextic function basically looks like a really, really weird function, because it has a degree of 6, it's not your typical quartic, that shit. So
An even function.
yeah,
That's the
it's
takeaway.
an even, yeah, because it's an even number. So you also have to consider the leading coefficient. The leading coefficient in this case is 2x minus 1 because of that order of 3. So the order of 3, now you have to look at the x-intercept. So the x-intercept for the leading coefficient is 1 over 2. The sign is positive. So you have an even function with a positive end behavior. So in even functions, their end behavior when it's positive goes from quadrant 2 to quadrant 1. If it was negative, it would be quadrant 3 to quadrant 4. So when we're graphing this function, you just got to account for those x-intercepts. Let me get my sussy pointer. So
That's such a
that's
beautiful
1.
function.
Yeah, that's 2. That is 3. We can also jot down our y-intercept, which is all the way down here. It will look roughly like this. Kind of ugly, kind of long. But yeah, you understand. So that's part 1. Determining the characteristics of k at x equals g at x over f at x. Now instead of multiplying two different functions, we're dividing one over the other. So step 1, factor. So g at x can be replaced with the original, so 2x minus 1, x plus 3, x plus 4. This was found back here when we divided it, factored up the bottom part, f at x, that was just as is. So now there are some key things we can do here. So x plus 3 is seen on the numerator and the denominator. Do a bit of canceling for those two. 2x minus 1 and 2x minus 1 are also seen on the numerator and denominator. Do a bit of canceling. You're left with x plus 4 over 2x minus 1. With this, you have the simplified version of k at x. Now you can determine some fun stuff. So like before, we have x-intercepts and y-intercepts. I don't know why there are two step 2s. Yeah, it's step 2 and step 2 and then step 3. So anyways, we got x-intercepts, y-intercepts. That's also a thing. Same thing. Just remember, factor out from the brackets y-intercept set x to 0. We also now have to consider vertical asymptotes and horizontal asymptotes now because the function is one over the other. There's probably a better way to explain that. You explain, AJ.
How to find a horizontal asymptote?
No. Why we have to find them?
Oh, because that's just how you graph it properly. So
Okay, all good. So
yeah,
vertical asymptotes, basically those exponential functions where the line barely touches that spot. Yeah, that's basically an
it
asymptote.
doesn't touch
Yeah,
it.
it just barely doesn't. It approaches barely. It will never
teases
touch it.
the asymptote.
Just like AJ's
Tickles the-
Riz. Okay,
Oh,
no, okay.
oh.
Vertical asymptote. Basically, it's the same thing as factoring out an x. Now you only have to do that for the denominator. So 2x minus 1, just take out the x, so you have 1 over 2. Therefore, there is a vertical asymptote at 1 over 2. Horizontal asymptotes. Okay, this one's a little tricky. So, y equals a over b. A representing the amount of x's on, is it the top or bottom? No. That's, yeah, the numerator. B representing the x's on the denominator. There is an x on the numerator and an x on the denominator. Wait, no, there's two x's on the denominator because of that that coefficient. So 1 over 2 is also the horizontal asymptote. If it's anything equal to the numerator, it will just be 0, right? Shouldn't it? Or if it's 1 over 1, wouldn't that just be 1?
Yeah.
Yeah, okay. Anything that's less than 1, 0.
I
Okay.
don't remember, man.
Yeah, so anyways, yeah, step 3, determine behaviors on VAs and HAs. So, your voice actor and behavior. Basically just substitute a value that's like roughly 1/10 higher and lower than your vertical asymptote. So 0.51 and 0.49. So when you input this into your actual function, so this shit here, you'll get either a positive or a negative value, and this tells you as x approaches 1 over 2 from the right, k at x should approach either positive or negative infinity depending on the value you get. I got positive infinity, so therefore k at x will approach positive infinity if x approaches 1 over 2 from the right. This is the same thing with x approaches 1 over 2 from the left side because of that small negative up there. I got a negative as well on this one, so all good. For your horizontal asymptote and behavior, it's the same thing, but since it's your horizontal asymptote, I don't even know why we just use 1k to represent infinity. So infinity is represented as 1000 and negative 1000 to represent negative infinity. So same thing, put that into your equation, and if your number is either positive, or no, if your number is either greater than 1 or less than 1, it will determine whether your function approaches your horizontal asymptote from above or below. Discontinuities, yep, that's a thing. Graphing k at x. So we have our x-intercept here and here, and we have our vertical and horizontal asymptotes. They're both at 1 over 2, both on x and y. There we go. Is there anything else I need to
Josh,
say? Yeah?
I've got there's we did it slightly differently. It doesn't really matter,
Yeah?
but I don't know. Maybe someone could spin this as an alternate solution.
Oh,
So it's oh wait, that's my docs. Where's my snipping tool?
sneep,
Aw.
sneep.
Yeah, where's my circumcision tool? Where are you? Oh, there we go. Okay. So yeah, what you did is you did like a bunch of you did like 2 test values.
Mm-hmm.
I think you really only need 1. So let me draw it with the graph. That looks disgusting. Let me draw it what the graph generally looks like. So we got our asymptotes here and here,
Mm-hmm.
but we also have our x-intercept
Oh,
at
I see, yeah.
-4,
Because I guess
and
you,
then
yeah,
hmm?
because you know where they'll end up because you have the x and y intercept. So
Yeah,
I guess doing those test values is just extra work.
so
It just
the one test.
further proves it.
Good.
Yeah. It just further
The
proves it. Yeah, keep going.
Oh, okay. The
Go ahead.
one test value that you actually should have though is the test value for uh 0.51. So that'll get you around here, and you'll know that it kind of looks like this
Yeah.
in the end. But yeah, that's pretty much it for the question.
Oh,
Except
so you do a little bit of less work. Wow.
yeah, that
Okay.
lazy gang.
Oh,
There's
lazy.
also part C to the question.
Yep.
Compare and
So,
contrast them.
what are similarities and differences from both h at x and k at x? So, some similarities. Both have an x-intercept with an order of 1. Wow. Both
Wow,
y-intercepts are below the x-axis. Wow. K at
wow,
x has
wow,
point symmetry at the origin 1 and 1. This is true right here.
wow,
That is directly symmetrical, reflected. Wow. Okay,
wow.
if the function is rotated 180 degrees, it coincides with the part of the graph on the other side. I think that is per spelling, I don't know. But yeah, if you reflect this on 80 degrees, it should be perfectly aligned with this one on the other side. Differences. They have different kind of end behaviors. This is true. Comparing k at x to h at x, there's clearly different end behaviors. This one has a end behavior from quadrant 2 to quadrant 1, whereas this one has end behaviors every direction. So, what's another one? K at x is
Um,
asymptotes, h at x does not. This is true because asymptotes are only seen on these funny looking functions.
there are
And
holes as well.
yeah, and there aren't other holes?
Yeah, there's a hole at
Oh yeah,
oh
there is a
I
hole.
I kind of spaced out. I didn't know if you mentioned the hole or not, but there's a hole at
But yeah,
-3.
isn't there a hole here and here?
Um,
Or
there's
would there
not a
be?
hole at
There would only be a
No.
hole here.
Yeah.
Okay. Yeah, there's a hole in x plus 3. Ah. Okay, so differences. Yeah, no, there's no point symmetry for h at x. H at x is just kind of cringe that way. It's a little zigzaggy. Yeah. But other than that, that's pretty solid. We've done question 2. Alright,
Yeah.
so we've done question 2. Moving on to question 3. Given f
Yeah.
at x equals x squared over that long function, determine the
Yeah.
domain, the intercepts, the asymptotes, and the behavior of the function here, its asymptotes, and then sketch. So,
Yeah.
we need to determine the domain, x and y intercepts, VA and HA, and the end behavior of the function around those asymptotes. Most importantly, we need to actually graph the function. So first, simplifying and finding the domain of f at x. Where's my trusty laser pointer? Why is my taskbar here? There, now it's gone. Doot, doot, doot. Where is it? Here you go. Laser pointer. So, find a factor for the denominator. We're going to have to do long division just like last time. You can also do synthetic division if your name is AJ Lovell. So, find a
Yes.
factor of 2 and 10. I didn't show it here because I'm too lazy, and also it's tedious. So, I got 1 over 2 as one of the factors. So, you have to factor 1 over 2 and set this equal to 0. So, bring stuff over, 2x1 or 2x minus 1 equals 0. That is now your dividend. Is it the dividend or divisor?
I don't know, man.
Dude, I don't care
forget.
as long as it works. So,
Yeah,
anyways,
cram,
yeah,
man.
you do
I don't
long
remember.
division. 2. We need to get 2 and 2 up here and up here. Okay, now that you've
Yeah,
done
just
that,
do long division.
yeah,
Or
you've done
you're
long division.
stupid.
Now everything on the top you need to factor. You factor that, you get this.
What?
Awesome. Make sure you have to state restrictions, also known as domain. So in this case, restrictions is everything in the denominator. 2x minus 1, x minus 5, and x minus 2. All of these are restrictions. So factor x out. You have restrictions of 1 over 2, 5, and negative 2. So x is the element of real numbers such that x cannot equal negative 2, 1 over 2, and 5. Alright, so other characteristics such as x-intercepts, y-intercepts, VA, and HA, these are all the same as question 2. You should know how to calculate these on your own, unless you're a brainian. Okay, all
Yeah,
good.
don't be
Yeah,
stupid.
all good. Just look at these values. They should be right. If it's wrong, you should hit me up, and I might lose it, because I'm going on Wednesday.
Wait, let me see. Let me.
Oh no,
I'll double
AJ,
check for you.
the inspector.
Yeah,
Yeah,
you've actually got everything wrong here. Yeah, there's
die.
the x intercepts are actually 12, 83, and 69.
Hey, we don't spread fake news in our math vids. Alright, behaviors of our voice actors and our head ass. VA. Vertical asymptotes, we have 3. 1 over 2, 5, and negative 2. These are all seen in the graph. See, there is one right here. I didn't show it. There's another one right here. They barely touch that point, but they kind of do look like that because I'm zoomed out. And there's one more right here at 5. So, 1 over, there's one here, negative 2, 1 over 2, and 5. So, same thing. You just got to make sure to find the behaviors of that using test values that are slightly above and below for your vertical asymptotes. For your horizontal asymptotes, 1000 and negative 1000 represent represent infinity and negative infinity, because you can't put infinity into a calculator. Yeah. So, graphing this function, yep, this is the same as the one before. This is your x and y intercept, 0 and 0, because before we have a convenience x and y intercept of 0. So, our function should look like this. The reason why this is kind of leaning a little closer to the intercept, like this line here and this one down here, it is because of that. Never mind.
I want to mention also something about the test values. You got to do a lot of test values. The teachers really hate you guys. So the ones I did were test values at -3, -1, 0.25, 2, and 6.
mhm.
But Morty, you gotta do a lot.
Yep.
Yeah, it sucks.
All right. So moving on to our next one. They're just misconceptions. Okay, we've done it. Oh my god.
말보다는 행동이지.
All right, so moving on to
Oh.
question 4. Miss Pact has a scrunchy side making business.
Thank you, Miss Pat. Very cool.
All right. Her revenue in thousands of dollars can be multiplied by the function r at x equals this. I don't want to say it to spare my voice. Where x represents the number of scrunchies sold in thousands. Once again, I don't know why she wrote it twice. Her cost can be multiplied by the function c at x equals 1 over x plus 3. So now we have to determine when Miss Pact breaks even and Miss Pact makes a profit. So,
In thousands.
yes. So breaking even is when the revenue R is equal to the cost of scrunchies. So R at X has to equal C at X. Whereas profit is whenever the revenue is greater than the cost of scrunchies. So whenever R at X is greater than C at X. Now there's an equality instead of an equal sign. We'll have to remember that. So first, we need to common factor and simplify R at X. Notice how R at X has a cubic power up there. We can't factor that out, so we have to common factor. So what do all three of these terms share? They all share a 5x. We can also take out negative 5 or a negative from the first term, so we have negative 5x on the outside, whereas this can now be common factored again. So 2x squared minus 3x plus 2, that can just simplify out to 2x plus 1 and x minus 2. Notice how there is a 2x plus 1 and a 2x minus 1 on both the numerator and the denominator. We can cancel those out, so we're left with negative 5x times x minus 2. Furthermore, we can also distribute this property into the brackets to simplify even more. Now we're left with negative 5x squared plus 10x. This is fully simplified.
You're a genius. I did it differently. They want multiple solutions. Do you want me to?
Yes, share
okay.
yours.
So, I'm just gonna say what I did because
Oh,
it's too much to write.
fine.
I saw you switch. Okay, so basically, I did big fraction, so negative 10x to the 3, blah 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 blah,
Mm-hmm.
minus
Oops.
the cost, and I just did that as one big ol' equation. And so basically, you want to find a common denominator. So that's going to be 2 times 2x plus 1. And then you're going to have a bunch of numbers on the numerator. I'm not going to read all of it. If you guys have any questions, just ask me. I'll be happy to send
You
a
gotta
screenshot.
send me this picture and I'll put it in this video when I edit.
The picture looks really bad. I'm going to have to
Rewrite it, Ben. Bozo. Okay, anyways.
it's
Oh,
readable.
okay. So Miss Pact breaking even. This is question A. Well, this is part of number 4. So Miss Pact breaking even. R at X must equal C at X. We have our recently new factored R at X, so now we can finally do some more math. C at X has already been simplified. So R at X equals C at X. First step, negative 5x squared plus 10x equals 1 over 2x plus 3. So first, we can simply convert the fraction into a decimal. This is one way to solve it. I don't know. I did it this way, so we ended up with different or the same values, just not in fractions. So we're working with decimals. Let's set the equation equal to 0. That means bringing all the terms on our right to our left, and also collecting like terms. We have 10x and negative 0.5x. That leaves us with 9.5x. Furthermore, am I missing steps here?
You want to factor it, I guess.
Wait, where did it go? Oh, here. Oh, I left the result up here. Okay, anyways, continued. We can common factor a... Oh, wait, never mind. This is how I did it. Yeah. To remove that decimal after converting from fraction to decimal, we just have to multiply both sides by 2. So 2 here and 2 here. Now we're left with a really nice and neat number of 19x. So negative 10x squared plus 19x minus 6 equals 0. Now we can factor this trinomial, blah, 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 what adds up to blah, blah, and multiply, blah, blah, we have 15x and 4x. Further factoring that out, we have 2x minus 3 and some remainders outside, and we can just merge them together to get negative 5x plus 2 and 2x minus 3. This is fully factored. So, if we want to convert this number into scrunchies, first let's factor out x from two of these brackets. Negative 5x plus 2 can be factored out to x equals 2 over 5. 2 over 5 in decimal form is 0.4. 0.4 times 1,000 will equal 400 scrunchies, because 1,000 is the scrunchies. Same with the other x-intercept. Well,
In thousands.
intercept. Yeah, in thousands. So 2x minus 3 equals 0. Now you have x equals 1 over 1.5. 1.5 times 1,000 will give you 1,500 scrunchies. That's a lot of scrunchies. I hope it was worth the money, Miss Pack. All right. A continue. This is what this function would look like. So c at x is the red line that's always increasing. R at x is that parabola. And over here we can see when she breaks even. When these two graphs intersect, well, not graphs, functions, when they intersect, we can notice that 0.4 and 1.5 are points where they break even. So we did our math right, which is good. These circled sections, they represent the breaking even parts. So therefore, Miss Pac must sell either 400 or 1,500 scrunchies to break even in sales. But obviously, we don't want to break just even. We want to break more money. Okay, what are you gonna say?
I have one thing to add. Also, if you go on Desmos and put the combined function into Desmos, so after simplifying it and everything, you should get a similar parabola. It's just that the x-intercepts are going to be at 0.4 and 1.5. But yeah.
Oh, very cool.
Ooh.
All right, moving on. Now, we want Miss Pac to make a profit, because selling even, or no, breaking even is cringe. You don't make any money. You just kind of stand there. So, instead of setting r at x to equal c at x, we're now going to add an inequality. R at x must be greater than c at x. We're going to do the same simplifying, and we'll be left with negative 5x plus 2 times 2x minus 3 is greater than 0. Just greater, not greater or equal to, because we already covered even. So we're going to factor out the same numbers, and now we're going to have 0.4 and 1.5, also known as 400 and 1,500. So looking at this graph here, we have a range. When she first broke even, and then when she broke even again, when she lost sales. Kind of sad. Anywhere in between this interval range is when she makes a profit. So I don't know why I didn't write. I never wrote the therefore statement. But anyways, yeah. Her range for breaking a profit is anywhere in between 0.4 and 1.5. So you could write this as x is an element of square bracket 0.4. No, not square bracket. Round bracket 0.4, comma, and 1.5. Circle bracket. That is whenever she makes a profit. We are done. No.
No, you, Miss Pat. Your business is doomed to fail.
Yeah, basically.